Hello everybody. So in this video, the things that we have to learn types of nucleophilic addition shown by aldehydes and ketones. So are supposed to know here is how many types of nucleophilic additions are there in aldehydes and ketones. So to start with, well, there is a simple nucleophilic addition. Simple nucleophilic additions means something is going to get added, and what is that? That is a nucleophile, Ne minus. Okay, a particular atom or a group having a negative charge. So in this case, what is happening is that there is no elimination of water. So as such, the thing that is going to be attached to this one, I mean whatever the nucleophile in this case, it is going to attach to the particular electrophile, and we have an addition product like this, right? Whereas in case of elimination of water, nucleophilic addition, where we have an elimination of water, say like what we have over here, it's like this nucleophile attacking on this one. Initially we have an addition, this is addition like what you have over here, but then the elimination also takes place. So it's a kind of a addition and elimination, right? So this is the thing, right? So elimination and addition. Okay, so we move forward and see what is the another thing. So these are the reactions that we have to study. Simple nucleophilic addition without elimination. So let's start with say addition of a sodium bisulfite. Sodium bisulfite is NaHOC3, and I have given the structure over here. It is SOH, right? Double bond O, and then ONA. Actually, it is a ONA. So actually, it is a if I would have written say like H2SO3, so it becomes sulfonic acid. So once it is a salt, so it becomes sodium bisulfite. Okay, and so what we see is that we have this O minus character over here, right? And but then sulfur has a lone pair of electron, right? So what happens is that this particular OH helps in formation of a double bond, and this particular, or you can also say like this, you have a lone pair of electron over here, because it is a salt, so it becomes kind of a double bond, and then this helps this particular sulfur, it releases its electron and it goes to the carbonyl group, so it get attached to this one, and this one becomes O minus, so salt, right? So how is it? It is a crystalline solid, right? So what happens is that aliphatic aldehydes, aliphatic ketones, aliphatic methyl ketones, or in other words simple ketones having a smaller size, and also also aromatic aldehydes, but then again I will say aldehydes only, no ketones. You see, this is a ketone, acetophenone, right? Benzene C double. This is not giving reaction with sodium bisulfite. So what I am trying to say is that sodium bisulfite, it forms a nucleophilic addition with a carbonyl or aldehyde group. If it is an aliphatic, right? If it is an aliphatic system, say for aldehydes and for ketones, then we are going to have an addition, and we are going to have a formation of a we can see this thing in form of a crystalline solids, right? These green marks. So this is for acetone, right? So you see this thing, these crystals, solid crystals are there, right? So this is case of in acetone. In benzaldehyde, you have a see this precipitate, solid precipitate, right, which is showing addition reaction. But in case of in benzaldehyde, it will be more of a kind of a oily solid, or oily solid kind of a thing. I mean more of a oil, but here it is it is crystalline solid. But in case of acetophenone, you will hardly see any solid formation taking place. It will be just a liquid only, right? So what I am trying to say for this particular addition for sodium bisulfite is that you will have an addition only for aliphatic aliphatic aldehydes, aliphatic ketones, Mind you, these are small, these are of small size, not much of sterically hindrance kind of a thing like this, right? And in case of a benzaldehyde, you can also observe this thing, right? For benzaldehyde also, because it is a smaller in size, you still have a hydrogen attached to this one, so addition uh, from this side can still take place because there's not much of a steric hindrance. But as the size increases, say it becomes CH3, we don't see any addition of such kinds. So this is the first thing to mark to keep in mind, because this particular reaction is going to help us in kind of a distinguishing between aromatic aldehydes and uh, aromatic ketones, right? Because aromatic ketones, they are not going to give. In fact, as the size increases for the ketone also, uh, this thing will become difficult. For aldehyde, aliphatic aldehyde, it is going to be very much easier, right? So we now see another slide. In this slide, we are showing the addition of a hydrogen cyanide. Okay, so HCN, this is HCN, right? So HCN is HC triple bond N. This is a weak acid. Okay, it has an inclination to give H plus and CN minus like this. Okay, but then it is a weak acid. So what you need is a strong base, right? You need a strong base. This is a weak acid. This is a weak acid. So you need a strong base, say like this. What it will help is that it will help in the generation of a CN minus, which can act as a nucleophile. So this is what is happening. So OH minus is helping you in abstracting this hydrogen plus proton, and eventually you have a CN minus, and this CN minus can attack on this particular carbonyl. Eventually, then you get this thing. This is a cyanohydrin. Cyano, this is CN, and hydrin is because OH. So this becomes cyanohydrin, right? Now, how are Grignard reagent and organolithium going to react with the system? This thing is we have already covered in Unit 1, metallic systems, Grignard and organolithium. We all know this R minus is going to attach to this one, right? And eventually we have a formation of a secondary alcohol. So there is no problem with that. Now, one important thing we are going to learn now, and this is addition of alcohol. Well, why it is interesting is because you see, well, when you have a, say like ROH plus RCOH, what does it become? RCOR, right? And then next is next what you are trying to do is now the interesting thing is that when you start studying organic compounds containing oxygen, so you start with functional group, say, of hydroxy, then you move on to CHO, CO, and then next to COOH and its derivative, right? And it could be anything, CN and blah blah, right? So this is on the left side, I mean reduced form. You oxidize it, becomes CHO, and further oxidize it, becomes this thing, correct? So you then end up over here. So you are adding alcohol and acid, formation of the ester. What happens when you start adding alcohol to an aldehyde, right? And this is an interesting thing because it has a huge practical applications, right? Especially in case of carbohydrates, right? You have a carbohydrates. I'm going to show about it, but for now, let's go back and just see what we are trying to see. So this is a aldehyde. This is a RCHO, and I am adding a alcohol. Now I need a acid, right? And I have taken HCl gas. This is dry, right? How does it help? Well, you have this thing, okay? So R, okay? Now H plus So it becomes something like this, okay, and this is nothing else, but you can also write it like this, R C this and OH, and you make it as a plus, because this is having a lesser number of electron, it will try to pull the electron towards itself. So eventually you have something like this, carbon becoming C plus, and then this one valency, I mean this is H, this is O, right? So this is after addition of H plus, it becomes something like this, and you have a plus charge over here. Now alcohol, which can act as an acid and a base depending on what it is reacting to, here now it start acting more like a nucleophile kind of a thing, because it has an electron, lone pair of electrons. So now it goes and gets attached to this one, right? So this has already become OH. So now this becomes R C H, and then OR dash, right? Getting attached to this carbon, and then this becomes OH. Actually it was like this, okay, RO dash, but then its oxygen valency is 3, so this gets detached, and eventually you have this OR dash, right? What do we call these systems? We call them hemiacetals. This is a hemiacetal, right? Why hemiacetal? Because only one RO dot alcoholic group has got attached in the form of alkoxy, and you still have one OH, right? So this OH, if it is reacting with say a strong base, will gets converted into alkoxide, O minus, right? And further reactions can take place, right? Now, or what can happen is that if you are reacting this OH with say stronger acid, then what can happen? It can become something like this, right? So that is what is happening in this case also. So you are adding this HCl, this H plus, right? It goes and gets attached to this one. So eventually it becomes something like this, OH2 plus. Now this is a good leaving group, right? I mean, you have this thing, and this would try to get out of the system, because then it forms a water molecule, right? It comes out of the system. So then what happens is that you have, so you have this system RCOH2 plus H, and then OR dash, correct? Now this wants to come out, so if it comes out, so it becomes something like this, RCH, you have a plus charge, you have a OR dash, right? And you have another molecule of alcohol. Now this lone pair of this oxygen having lone pair of electron, it goes and gets attached to this carbon, and so you have this particular formation taking place, right? Now mind you, this is an equilibrium, this is a reversible reaction, right? So here you have a hemiacetal because you had one OH, but if this OH also gets converted to OR dash, then you start calling it as an acetal. And again I remind you that this is a reversible reaction. This system is stable in basic mediums only, right? In basic mediums only, right? Because once you have an acidic thing back, say this one, right? It's going to again get converted back to ketones, say like this getting converted acetal to hemiacetal, and then acetal to alcohol. Actually, you see, this particular thing is exploited in the protection of the you can say alcohol also if required. If you want to protect your ROH group, you don't want to get it reacted, so you can kind of save it by reacting it with a something ketonic molecule, and you can eventually convert to acetal, and the vice versa also. If you want to kind of protect your aldehyde, employ this strategy also. So this is about acetal. Now let's move forward and see this particular reaction, this particular slide. Actually it is extension of the last one, and here I'm trying to show you the importance of the hemiacetals, acetals and hemiacetals, right? So we just saw how hemiacetals are formed and how acetal is formed, and it is stable in basic medium, right? Correct. Now we have a Benedict test. What it does is verify the presence of a reducing carbohydrate. Reducing carbohydrate means say like sugar, say like sucrose, right? So you need to have a one particular OH group that is free. Then you call it as a reducing carbohydrate, because I mentioned that once you have a hemiacetal, this OH is free. So these are kind of a reducing carbohydrate because it can get now converted to OR dash, right? This can, as I showed you earlier, I mean, if it is, if you have something, say like kind of a RX kind of a system, this is plus, this is minus, so it gets attached to this one. So this system, this is a non-reducing system, but this is a reducing system, right? Reducing carbohydrate kind of a thing. So compounds having hemiacetals in their structure. So this, which we have hemiacetal, this is a reducing carbohydrates. So it has a huge application in carbohydrates. So here I again show you this thing. Say like I have a one particular carbohydrate. So here you see this thing. Now one particular thing by which you can identify you have a acetal presence at a particular for a particular compound is just by looking at one particular carbon. If one particular carbon is attached to two oxygen groups, say like here, this is getting attached to the, earlier it was double bond O, right? Or maybe you have a COH only, right? Alcohol, one particular oxygen group. But if you have a two oxygen group attached to a one particular carbon atom, initially this is hemiacetal, but then this is acetal, right? So you have a two oxygen attached to one particular carbon. What do you expect such systems to be? Is it going to be stable for a longer time? No. Why? Because this is a minus and this is plus. This again is a minus. So it makes kind of as a double carbon system, which is having a less electron density onto this particular point, right? So they are more kind of a reactive, right? So in this particular system, we want to check whether we have a hemiacetal at a particular point. So we just see this particular carbon and we find this is attached to two oxygen, this oxygen and this oxygen. Let's see over here again, this oxygen and this oxygen, and this oxygen, one particular oxygen is a OH. So it is a reducing carbohydrate because it can further, I mean, this hemiacetal can further become acetal, say like this. But now here you see this is OCH3, so this is acetal. This was hemiacetal, right? So you have a, say like this particular carbohydrate, you treat it with a base. What does the base do? Now first of all, try to see whether we have a hemiacetal center over here or not. So this particular carbon, you see two oxygen attached to it. This is one and this is one. So this is a hemiacetal carbon, hemiacetal system with one particular carbon having two oxygen group, and this is one, this is OH. So in presence of a base, what does happen? It becomes kind of a O minus, and then it opens up the ring system, because this becomes, this O minus becomes double bond O, and then this thing goes over here, something like this. So you have a hemiacetal, so base comes. What will base do? Base will abstract this proton and then becomes O, right? Now what will do this? This becomes C double bond O, and eventually this goes off, right? So this ring ring destruction, ring opening kind of a thing takes place. So in case of a Benedict test, we treat it with a base, right? Ring opening is taking place. You have a copper salt, and this copper salt, what does it do? It gets this is Cu2 plus, right? It eventually forms a red precipitate. So what is happened over here is the ring opening has taken place, right? So this concept of acetal has a huge importance. In fact, if you remember, we have learned about this system in the one among the last videos, I guess, 1,3-diethiene system. You remember we had this thing, aldehyde, right? And eventually what was happening was like this. So we had 1,3-diethiene formation, correct? So this become H, this become S, right? Now this, but you see this carbon is attached to two sulfur, right? Now do you see any analogy with the present system, this one? So we have, if we have like this, right, this is a hemiacetal, right? But if we have again R and R, this becomes acetal, right? So like this one was OH, then this was hemiacetal, and then it gets converted, it becomes acetal, right? So we know we are seeing acetals are reversible. They gets converted to hemiacetal and then aldehyde also. Now in periodic table you have sulfur just below the oxygen, so it is also going to behave in the manner in which oxygen is behaving. So you have, say, if you just replace SH by OH, so you can clearly see that here we have a kind of a acetal formation, but since this is a sulfur, so we call it a dithioacetals, right? So we have already seen its application. What? Because in presence of a base, what it was happening was like something like this. This is sulfur, this is sulfur. It was becoming like this, and you can then allow it to react with the RX. So you had then something like this R, right? 1H is still free, you can then get it converted to R, and then you hydrolyze this system, because this is sulfur, it's going to get dissociated very soon, and then you get back this thing. So you started with a kind of a very small aldehyde having very less number of carbons. You get H substituted through 2R, right? So this was for the 1,3-dithiene, but the analogy is same for the acetals, right? In this particular picture, what we are showing is that when we are reacting Benedict solution in a boiling water bath with sucrose and glucose, then in one case we are seeing a negative result, in another case we are seeing a positive result. Okay, so sucrose, this is a sucrose thing, and this particular test tube contains glucose. We add Benedict solution to it, and or vice versa. So in case of sucrose we are seeing a negative result, right? But in case of glucose we are seeing a positive result. And what we saw in the last slide was that Benedict solutions gives a positive test for reducing sugars. So it is giving positive test for the reducing sugar, for the glucose, and I was mentioning that you need to have a COH group kind of a thing. So that will be a hemiacetal thing, right? So that will be reducing. That can show reducing character. So that means it will give a positive test for the Benedict solution, right? Now see it for the glucose. So first of all, we need to find the particular carbon center by which we can say it as a acetal or hemiacetal kind of a thing. So how do we know that we have a hemiacetal or acetal kind of a thing in our compound? We have to search for a carbon containing 2 oxygen atom attached to it. So this particular carbon center has a 2 oxygen atom. One is this one, and the second is this one. And over here we see this carbon center. So this one has been a 1 oxygen and another oxygen. Similarly here also 1 oxygen and 1 oxygen, right? So here what we are finding is that both of these carbon center, though they have oxygen attached to it, but they are enomer. Say like these are OR kind of a system, right? We don't see this kind of a thing in the sucrose, but in case of glucose we are seeing at least one OH group is there. So this will be called as a reducing sugar, right? And that is why it gives a positive test for the Benedict solution. So the application of the acetal and hemiacetal in order to determine the reducing character of sucrose and glucose comes very handy in such things. So this particular picture does give this, it all depicts all these things. This OH coming from this O oxygen, and then you have this NHG for NHG formation taking place, right? And eventually when the water molecule gets released, how something like say like you have H, right? So it goes here. So H, it comes out in the form of a H plus. This goes here, and then this comes out. So H plus and OH minus. So this is minus H2O, and eventually you have this thing, C double bond Ng. So we call it as a imine bond, right? Very important thing, very important thing. Why? because the vice versa also takes place. I mean, you hydrolyze it, so you then eventually get something like this. So it becomes carbonyl, and then you have a NH2G kind of or ammonia kind of a thing formation. So from ketone you can form imine, and similarly from imine you can get back carbonyl. So this imine hydrolysis gives you carbonyl and amine group derivative, amino group derivative, right? So this G can be OH. So if you have a OH, it is called hydroxylamine. This gives you oxime, right? If it is NH2, it becomes hydrazine. If it is this, then phenylhydrazine, because you have pH attached to this one, so it becomes phenylhydrazone. Then you have a 2,4-dinitrophenylhydrazine, right? Okay, so we see that so we have a say like okay, so we see this as when we have a phenylhydrazine, so we have phenylhydrazone. Now this is Brady's reagent. What is that? It again is a phenylhydrazine, but then you have a 2 nitro groups, right? 2,4-dinitrophenylhydrazine, right? So this is this, right? And when this addition 2,4-DNP, it's get attached to carbonyl, you have a 2,4-dinitrophenylhydrazone formation, and also the same with semi-carbazide, right? So you have a semi-carbazide, and this is NHCONH2, right? NH2 attached to NHCONH2, right? Reminds us of urea, right? This particular thing. Then this is semi-carbazone. All these are colored solutions, so yellow, orange, or red, right? So crystalline solids, and these are used for identification of aldehydes and ketones. Okay, so yeah, next we see reaction of ammonia with aldehydes, and next we see reaction with ammonia of the aldehydes, and this is a ketonic group, and we are adding it to ammonia in ether, and this is carboamine, OH and NH2. So this with the release of the water, we have a imine bond formation, right? We call it as acetaldehymine, and it polymerizes to this particular polymer, right? So if we have 4 molecules of ammonia and formaldehyde, right? So we get that this urotropine, which has a medicinal use. So it is a hexamethyl tetramine. So this is like this. Why it is important? Because once we attach nitro group to this system, right? It becomes something like this. We have a 3 nitro group, and all the explosives they have one particular common thing. It is the presence of nitro group. So all explosives, right? They have this nitro kind of a thing. So this is RDX full name is Research and Development Explosive. Okay. Now we come to the next one, and here we see Benzaldehyde reacting with ammonia. Okay, and so these are 2, 1, 2, and third molecule of Benzaldehyde reacting with ammonia, and then we have a hydrobenjamide, and now in this one we are attaching ammonia to carbonyl group, so we again have a carbolamine kind of a thing, and we are reacting with acetone, so we get this kind of thing. Okay, so what we have come to know in this particular chapter is that we have a carbonyl group, and it can get attached, can get with 2 types of reaction, in which we have elimination of water, and in another one water is not as such. The system have things in which we have say like one particular group keeping attached onto this kind of a system, right? So we have seen all kinds of this thing reaction, right? So like sodium bisulfide, these are addition reaction. So we have seen that we will have addition reaction and we can have elimination in the fifth reaction, right? So this is all about the types of addition reaction. Okay. Thank you.